Today's topic is Introduction to Machine Learning in that PAC Learning. So, what is PAC Learning? Understanding PAC Learning, like where, where it is used, theoretical foundations and practical applications in machine learning. And in the vast landscape of machine learning, understanding how algorithms learn from data is very crucial and probably approximately correct that is the probably approximately correct, that is a PAC learning stands as a cornerstone theory, offering insights into the fundamental equation of how much data is needed for learning algorithms. Two reliable, generalized, to unseen instances. Pack learning provides a theoretical framework that underpins many machine learning algorithms. By delving into pack learning, we gain a deeper understanding of the principles guiding algorithmic decision making and predictive accuracy. So, take a table of contents like here, these are the topics that we will be discussing in this video. So what is pack learning? Probably approximately correct. That is pack learning is a theoretical framework introduced by Leslie Valiant in 1984. It addresses the problem of learning a function from a set of samples in a way that is both probably correct and approximately correct. In simpler terms, pack learning formalizes the conditions under which a learning algorithm can be expected to perform well on new, unseen data after being trained on a finite set of examples. Backlearning is concerned with the feasibility of learning in a probabilistic sense. It asks whether there exists an algorithm that, given enough examples, will find a hypothesis that is approximately correct with a high probability. The probability aspect refers to the confidence level of the algorithm, while the approximately a correct aspect refers to the accuracy of the hypothesis. And importance of back learning, probably approximately correct. That is, back learning is important because it provides a rigorous foundation for understanding behavior and performance of learning algorithms. It helps to determine the conditions under which a learning algorithm can generalize well from a limited number of samples, offering insights into the trade-offs between accuracy, confidence, and sample size. The PAC framework is widely applicable and serves as a basis for analyzing and designing many machine learning algorithms. It offers theoretical guarantees that are crucial for assessing the reliability and robustness of these algorithms. By understanding pattern, researchers and practitioners can develop more efficient and effective models that are capable of making accurate predictions on new data. Core concepts of pack learning, sample complexity. Sample complexity refers to the number of samples required for a learning algorithm to achieve a specified level of accuracy and confidence. In pack learning, sample complexity is a key measure of the efficiency of a learning algorithm. It helps determine how much data is needed to ensure that the learned hypothesis will generalize well to unseen instances. The sample's complexity depends sorry, the sample complexity depends on several factors, including the desired accuracy, confidence level, and the complexity of the hypothesis space. A higher desired accuracy or confidence level typically requires more samples. Similarly, a more complex hypothesis space may require more samples to ensure that the learned hypothesis is approximately correct. And hypothesis space. The hypothesis space is the set of all the possible hypotheses or models that a learning algorithm can choose from. In fact, learning, the size and structure of the hypothesis space play a crucial role in determining the sample complexity and generalization ability of the algorithm. A larger and more complex hypothesis space offers more flexibility and can potentially lead to more accurate models. However, it also increases the risk of overfitting where the learned hypothesis performs well on the training data but poorly on new unseen data. The challenges on back learning is to balance the flexibility of the hypothesis space with the need to generalize well. And generalization is the ability of a learning algorithm to perform well on unseen data. In the PAC framework, generalization is quantified by the probability that the chosen hypothesis will have an error rate within an acceptable range on new samples. Generalization is a fundamental goal of machine learning as it determines the practical usefulness of the learned hypothesis. A model generalizes well can make accurate predictions on new data, which is essential for real-world applications. The PAC framework provides theoretical guarantees on the generalization ability of a learning algorithm, helping to ensure that the learned hypothesis will perform well on the data. And PAC learning theorem, the PAC learning theorem provides formal guarantees about the performance of the learning algorithm. It states that for a given accuracy, there is no confidence interval, there exists a sample size n that such that any learning algorithm that returns a hypothesis consistent with the training sample will with probability at least 1 minus delta have an error rate less than epsilon on unseen data. Mathematically, the pack learning theorem can be expressed as m greater than or equal to 1 by epsilon of log 1 by delta plus Vc of h, where m is the number of samples, is the desired accuracy, and delta is the desired confidence level. Vc of h is the Vapnik Chernow-Nenekis dimension of the hypothesis space H. Mathematically, the pack learning theorem can be expressed. So we have seen the above. Please refer to the above one, and where so we have already described what it is, and the VC dimension is a measure of the that is the VC is nothing but Vapnik Chernow kids dimension is a measure of the capacity or complexity of the hypothesis space. It quantifies the maximum number of points that can be shattered, that is correctly classified in all possible ways by the hypothesis in the space. A higher VC dimension indicates a more complex hypothesis space, which may require more samples to ensure good generalization. The pack-learning theorem provides a powerful tool for analyzing and designing learning algorithms. It helps determine the sample size. It helps determine the sample size needed to achieve a desired level of accuracy and confidence, guiding the development of efficient and effective models. Challenges of back learning, real world applicability, while back learning provides a solid theoretical foundation, applying it to real world problems can be challenging. The assumptions made in the back learning, such as the availability of a finite hypothesis space and the existence of a true underlying function, may not always hold in practice. In real world scenarios like data distributions can be complex and unknown, and the hypothesis space may be infinite or unbounded. These factors can complicate the application of back learning, requiring additional techniques and considerations to achieve practical results. Computational complexities, like finding the optimal hypothesis within the back framework, can be computationally expensive, especially for large and complex hypothesis spaces. This can limit the practical use of back learning for certain applications, particularly those involving high dimensional data or complex. Efficient algorithms and optimization techniques are needed to make back learning feasible for practical use. Researchers are continually developing new methods to address the computational challenges of back learning and improve its applicability to real world problems. Modern assumptions like back learning often assumes that the data distribution is known and that the hypothesis space that use the true function. These assumptions can be restrictive and may not always align with the real world scenarios where data distribution are unknown and the true function is not within the hypothesis space. Relaxing these assumptions and developing more flexible models is an ongoing area of research in machine learning. Advances in this area can help make back learning more robust and applicable to a wide range of problems. Practical example with code. Import NumPy as NP from SK-learn model selection important input training test aspect. So this is a program where it will we are here we are importing the required libraries, and here we generate synthetic data sets with this particular code, and then we are splitting the data set into training data set and as well as the testing set. So here is the one which we are splitting for training and testing. And next is the train and decision tree classifier, CLF decision tree classifier, and we are just inputting the data. So X train the training data and Y train data, and predict on the testing data. So what from the predictions like calculate accuracy like equal to accuracy score of Y test and Y predictions. Functions to evaluate model performance with varying training set size. These are the functions like, and for train size in train sizes, these are the codes. And here we are trying to find the CLF patient tree classifiers, and also we trying to fit those data training like extrain and retrain, and the predictions we are doing with CLF or predictor test. So evaluate sample complexity. This is the here we are trying to evaluate the samples complexity of the given data set, and then we are trying to plot the results to find produce a graph where we can easily see the training set size, accuracy, sample complexity, and accuracy, and whether it is true or false. So this is how the that plot will look like. So these are the accuracy on the test set with 80% of the data used for training. Accuracy is 0.91. Training set sizes and corresponding accuracies, these are the ones. So based on the size, the accuracy we can compare. So these are also the various set training set sizes and the relevant mechanisms. So conclusion is like PAC learning is fundamental theory in machine learning that offers insights into the sample complexity and generalization of the algorithm by understanding the trade-off between accuracy, confidence, and sample size. PAC, which is probability approximately correct learning, helps in designing robust models despite challenges such as computational complexity and real-world applicability. It provides theoretical guarantees to show for reliable model performances and practical applications, as illustrated through the patient examples. So, how increasing training data improves accuracy, highlighting the importance of sufficient data for effective learning. Pack learning remains vital for developing efficient algorithms capable of accurate